Hello students, today we are going to discuss about the concept of special matrices. We are going to see some special matrices which are based on the concept of symmetry. Okay, so there are matrices like symmetric matrix, skew symmetric matrix, orthogonal matrix, and in the complex matrices we have Hermitian matrix, we have skew Hermitian matrix and unitary matrix. So it is very important in the case of GATE examination. So that is why we are going to emphasize on this particular topic. Now the questions that are framed in the GATE examination based on this particular topic are not difficult, they are on the easier side. So let us first of all see the basics that are required to understand the concept of special matrices. Okay, so the basics that are required to understand this particular concept is that you should know about A, the matrix representation, how the matrix is represented. Second thing, you should know about what is a principal diagonal element. Third thing, we should know about the transpose of a matrix. What is the meaning of a transpose? And of course, we should also know about transpose of conjugate. So these are some basics that are required that we are going to use in understanding the concept of special matrices. So first of all, let us look about what is a matrix representation. We all know that matrix is going to be a very important mathematical entity. It is basically used to arrange the numbers or variables or any constants or any function in terms of rows and columns so that we can have a data which is going to be properly represented. So we can say in simple that a matrix is nothing but the data that is arranged in rows and columns. For example, if I want to represent a matrix A which is written in terms of rows and columns, so I can have it in terms of A11, A12, so on, A1n. Similarly, A21, A22 and so on, A2n, and so on, AM1, AM2, so on, AMN. So what I am trying to do here is that I am trying to arrange some elements in terms of rows and columns. So here you can see that how many rows are present? There are m number of rows and n number of columns. Okay, so right, I am going to have m number of rows and n number of columns. This m by n that we are writing is what we call as the order of a matrix. M by n is nothing but a order of a matrix where m is nothing but number of rows and n is going to represent number of columns. And I can simply write the matrix A can be simply represented as Aij, where I is the row number and j is the column number of m by n. So I is nothing but the row number and j is the column number. When the value of m is equal to n, we call the matrix as a square matrix. When the value of m is not equal to n, we call it as a rectangular matrix. We call it as a rectangular matrix when the value of m is not equal to n. When it is equal to n, then we can say it is going to be a square matrix, and in general we are going to use many of the cases only the square matrix. So even in the special matrix that we are going to learn, all of them are going to be only square matrices. So that is the importance of this one, the square matrix. So this is how we can have a representation of a particular matrix. So every time we have a matrix, when we want to take an example, we consider a capital alphabet A is going to represent a particular matrix. Now, what is the principal diagonal element of a particular matrix? Okay, what are the principal diagonal elements of a particular matrix? We have seen here that we have a matrix A that can be represented as Aij m by n. Now, the values where the row number is equal to column number, those elements are what we call as the principal diagonal elements. So the elements of a particular matrix where the row number is equal to the column number, so such a particular element is what we call as a principal diagonal elements of a particular matrix. Now for example, here if you observe, the row number is equal to the column number. Here also the row number is equal to the column number. So every time when the row number is equal to the column number, we can call them as the principal diagonal elements of a particular matrix. So for example, if I take a square matrix A which is equal to 1, 2, 3, minus 1, 1, 0, 3, 2, 1. Now these three elements are same and are equal to 1. Now all the three elements are what we call as the principal diagonal elements, because here for these elements the row number will be equal to the column number. So here the row number is 1, the column number is 1. Here the row number is 1, the column number is 1. The row number is 2, column number is 2. Here the row number is 3, the column number is also 3. Okay. Now the third one is the transpose of a particular matrix. Now what is the meaning of transpose? Transpose, in the operation of a transpose, we just try to interchange the rows and columns of a particular matrix. So whenever we interchange the rows and columns of a particular matrix, we call it as a transpose of a particular matrix. So when I have a matrix A, which is given by Aij m by n, okay, in that case A transpose is going to be equal to the transpose of this one is now going to be equal to Aj n by n. Okay, so A transpose is nothing but interchanging the rows and columns. So row and columns are interchanged here. We're going to have a transposed matrix. Now for the example that we have considered here, the matrix A, which is 1, 2, 3, minus 1, 1, 0, 3, 2, 1. Now the transposed matrix A transpose will be equal to, now the row will become column and the column is going to become row. So now I can write 1 minus 1, 3 is going to be the first row, because the first column is going to become the first row here. And similarly the second column is going to become the second row. 2, 1, 2. The third column is going to become a third row here. 3, 0, 1. So this is my A transpose. Okay. So transpose is nothing but whenever you are applying the mathematical operation of transpose, rows and columns are going to be interchanged. Okay. It's a 3 by 3 matrix. So here also you will have a 3 by 3 matrix. If you have a 2 by 3 matrix, the transpose is going to be a 3 by 2 matrix. Okay. So the number of rows are going to become number of columns and vice versa. Now what are the properties of the transpose that we generally learn is that A transpose whole transpose is equal to A. Nothing but the properties. And AB whole transpose is equal to B transpose into A transpose. And A plus B whole transpose is equal to A transpose plus B transpose. These are three very important properties of the transpose. Okay. So we have learned about the first three, and the last one now is the transpose of a conjugate. Transpose of a conjugate. So what is the meaning of conjugate? See, we will discuss about the concept of conjugate only in the case where the matrix is going to be a complex matrix. Now whenever all the elements of a particular matrix are real numbers, then the matrix is automatically a real matrix. Now whenever you are talking about a conjugate, it means that we are talking about the complex matrix. Because for a real number, the conjugate is going to be the same. So in such a case, we are not going to emphasize on the conjugate. But a conjugate, the importance of conjugate will come into picture only in the case where the matrix is going to be complex in nature. Okay. So for example, if I have a number A which is equal to 1 plus J, its conjugate is going to be 1 minus J. Now similarly, if I have a matrix A which is equal to the top, let me consider a 2 by 2 matrix. 1 plus J minus 1 plus J, 3 plus 2J, 2 plus J. So it's a 2 by 2 matrix. I want to apply the conjugate. A bar is equal to the top. I have to just take the conjugates of a respective elements. So here it is 1 plus j, it is going to be 1 minus j. Here it is minus 1 plus j, it is minus 1 minus j. 3 plus 2j, 3 minus 2j. 2 plus j, 2 minus j. So the conjugate matrix will be each and every number individually. You have to take the conjugates. It's going to give the conjugate of an entire matrix. Now we are going to discuss about transpose of a conjugate. So we are applying the transpose to the conjugate. We already have a matrix for which we know its conjugate, and now for the conjugate we are going to apply the transpose. So we call this a transpose of a conjugate. So A bar whole transpose, we simply call it as A theta. In negating, it is the transpose of a conjugate. So now already I have a bar. Now the transpose is going to be, just the rows and columns are interchanged. So 1 minus j, 3 minus 2j, minus 1 minus j, 2 minus j. Okay, so this is going to be the transpose of a conjugate. So these are the basics that are required to understand the special matrices that we are going to discuss in this session. So the reason why the special matrices are really special is because these matrices are going to make the analysis that we are going to do mathematically very simple. So every time we have a general matrix, we try to search for the symmetry inside the matrix. Okay, so the first matrix that we are going to learn here is a symmetric matrix. What is the meaning of a symmetric matrix? Symmetric matrix is simply a matrix whose transpose will be equal to the matrix itself. When the transpose of a matrix, if it is equal to matrix itself, then we call the matrix is going to be a symmetric matrix. A transpose is equal to A, we call it as a symmetric matrix. Now, what does it mean actually? If I know that the matrix A is going to be Aij m by n, now the transpose is going to be equal to that of Aji n by n. It means that the element Aji should be equal to Aij. Aji should be equal to Aij. It means that, for example, if I have A21, A21 is going to be equal to A12. Similarly, if I have A31, this will also be equal to that of A13, and A23 or 32 is going to be equal to that of A23. Because it is satisfying the Aji is equal to Aij. What is I and J? I and J are nothing but the row number and the column number. So A12 is going to be equal to A21, or A31 is equal to A13, A32 is equal to A23, and A11 is equal to A11 because of the fact that both are same. So A11 is equal to A11, A22 is equal to A22, A33 is equal to A33. So that doesn't make any sense. So now I can simply write a symmetric matrix after knowing the property of the symmetric matrix. It simply means that Aji is equal to Aij. After applying the transpose of the matrix, still the matrix is not going to change. The matrix is going to be identical even after applying the transpose on a particular matrix. So now, for example, I know this is going to be A11. So A11 is 1, for example. A12 is 2. And A13 is 3. Now A21 is equal to A12. It means that here also you are going to have 2. A31 is equal to A13. So here also I am going to have 3. So whatever element I have, this is A13. So now this A31 is also going to be equal to that of A13. And there is no restriction on the principal diagonal elements. Whenever the value of I is equal to j, we call them as principal diagonal elements. So there will not be any difference in the principal diagonal elements. Now, if you observe here, -1, 0. It doesn't matter, or there is no restriction on the principal diagonal element in the case of a symmetric matrix. Now, the moment I write this value is equal to 4, what is this element? This element is nothing but the second row and third column. So A23. And we know that when you write A32, A32 is equal to A23. So if I write 4 here, here also you're going to have 4. So in this way, I can simply write the symmetric matrix. Symmetric matrix is nothing but when you're applying the transpose on a matrix, you're going to have the same matrix. Now if you observe, all the symmetric matrices are going to be the square matrices. You cannot take a rectangular matrix and still try to satisfy the symmetry, because it is very important that the order of the matrix is going to be a square matrix. So now if you apply the transpose on it, no doubt it will satisfy A transpose is equal to A. So 1, 2, 3, 2 minus 1, 4, 3, 4, 0. If you observe, it is identical to the top, the matrix that we have written. So this is how the symmetric matrix is going to be. Now the second type of matrix that we are going to discuss is a skew symmetric matrix. So we can also call the skew symmetric matrix as an anti-symmetric matrix. We can also term it as an anti-symmetric matrix. So what is the property that the skew symmetric matrix is going to satisfy is that the transpose of a matrix will be equal to the same matrix but with a negation. The transpose of a matrix will be equal to the same matrix with a negation. That is what we term it as a skew symmetric matrix. A transpose is equal to minus A, we call it as a skew symmetric matrix. Now what does it mean? We know that for the matrix A, which can be written as Aij m by n. Now the transpose is going to be equal to the top Aij or Aji n by m. Now, the moment you write A transpose is equal to minus A, when you are equating the matrices, the only important thing is that their order has to be the same. Okay, so it means that it has to be a square matrix. If the orders of A transpose or A transpose is equal to minus A, when you are equating two matrices, their orders has to be the same. And we know that here in this case, it has to satisfy once again the square condition, the square matrix. It has to be a square matrix here. So A transpose is equal to minus A. It simply implies that Aji is equal to minus Aij. When you are equating these two, A transpose is equal to minus A, it means that Aji is equal to minus of Aij, considering that the order of the matrix are same, it means that it is a square matrix. Right? So Aji is equal to minus Aij is a condition that a skew symmetric matrix has to satisfy. Now if I write both I and j both are equal to 1, it means that A11 is equal to minus A11. In the case of a skew symmetric matrix, if I am talking about a single principal diagonal element, that is A11, the row number is 1, the column number is 1. So A11 should satisfy it equal to minus A11. Can you tell me when this is going to happen? That an element is equal to the element with a minus sign. This can only happen with a single number, and the number is nothing but 0. Okay, for no other number this is going to satisfy. That A11 is equal to minus A11 is going to be satisfied only when the number itself is 0. So it means that here it has to be 0. Now A22 is equal to minus A22. This is also equal to 0. A33 is equal to minus A33. This is also equal to 0. Okay, so all the principal diagonal elements in the case of a skew symmetric matrix are equal to 0. All the principal diagonal elements are equal to 0. That is the first property if you observe in the case of a skew symmetric matrix. Now let us come to the other elements apart from the principal diagonal elements. For example, if I am talking about A21, now A21 is equal to minus A12. A21 is equal to minus A12. A31 is equal to minus A13 and A32 is equal to minus A23. This has to be once again satisfied. So now I can write a simple example matrix. If I have A is equal to, once again I am considering a 3 by 3 matrix, okay, a square matrix. Now I know that the principal diagonal elements have to be equal to 0. Here the restriction is there on the principal diagonal elements, unlike the case of the symmetric matrix. So all the principal diagonals are equal to 0. All the principal diagonal elements are equal to 0. Now if I write A12 is equal to 1, what is the value of A21? A21 is equal to minus of A12. We know A12 is equal to 1, so A21 should be equal to minus 1. If I write this element as equal to 2, now what is this element? A13. So A13 is equal to 2, it means that A31 should be equal to minus 2. Now if I take the value of A32 or A23 is equal to 4, here I should have minus 4. So this is how we can write a skew symmetric matrix based on its property. Now you can see that the transpose of a matrix will be equal to, just interchange the rows and columns. So it is 0, minus 1, minus 2, 1, 0, minus 4, 2, 4, 0. Bring the minus outside. Okay, so you're going to have 0, 1, 2, minus 1, 0, 4, minus 2, minus 4 and 0. If you compare, it is exactly is equal to that of minus A. Okay, this matrix is A, you have a minus sign, so it is minus, correct? So A transpose is equal to minus A, which will be satisfied in the case of a skew symmetric matrix or an anti-symmetric matrix. So a general matrix which does not satisfy both of the cases, it means that it is neither symmetric nor skew symmetric. That is what we call as a non-symmetric matrix. So a non-symmetric matrix is a matrix which is neither symmetric nor skew symmetric. It means that A transpose is not equal to that of plus or minus A. We know that A transpose, if it is equal to plus A, we call it as a symmetric matrix. When the A transpose is equal to minus A, we call it as a skew symmetric matrix. If neither of them is going to satisfy, it is a non-symmetric matrix. So now let us see the gate problems on these three matrices. And the questions are really straightforward. It's a simple theory question. A square matrix B is skew symmetric. Okay, so here a square matrix B is skew symmetric if B transpose is equal to minus B, B transpose is equal to B, B inverse is equal to B, B inverse is equal to B transpose. And we have just now seen the answer is option A. Okay, now let us look at the other options. Is there any learning that we can have from the other options? B transpose is equal to B, what does it mean? When B transpose is equal to B, it is nothing but a symmetric matrix. B inverse is equal to B. Whenever the inverse of the matrix is equal to the same matrix, we call the matrix as a involutory matrix. When the inverse of the matrix is equal to the matrix itself, we call it as a involutory matrix. Also we can say it as B square is equal to I. Both are one and the same. B inverse is equal to B or B square is equal to I. Both mean the same. Now for example, I is the identity matrix. So B square is equal to I. Multiply with B inverse on both sides. On both sides try to multiply with the of B inverse. So it is B inverse into B square is equal to I into B inverse, which is nothing but B inverse itself. So identity matrix, when you are multiplying with any matrix, we are going to have the same matrix. So you're going to have B inverse. So B inverse into B square is nothing but, we can write B square as B into B. So B into B inverse is going to be equal to I. So we're going to have B is equal to B inverse. This is because when you're writing this one, we can write it as B inverse into B into B. B square is equal to B into B. So B inverse into B. Any matrix multiplied with inverse is going to be its identity matrix. So I into P is going to be B itself. So B is equal to B inverse is nothing but the property that we are looking for, which is involutory matrix. Now there is one more special matrix which is nothing but B square is equal to B. When the B square is equal to B, we call it as a idempotent matrix. Whenever B square is equal to B, we call it as a idempotent matrix. Okay, so this is an involutory matrix that is given in the option. B inverse is equal to B. We are going to see shortly that is nothing but an orthogonal matrix. Now even the second question is also theoretical in nature. So this is also a gate question. Which of the following is true? So the question given here is that which of the following is true for a matrix A which is written as Aij m by n. First statement is that for a symmetric matrix Aij is equal to Aj. For a symmetric matrix Aij is equal to 0 for I is equal to j. This is the second statement. The third statement is for a skew symmetric matrix Aij is equal to minus Aj. The last one is that for a skew symmetric matrix Aij is equal to 0 for the value of I is equal to j. So the options which are given here are 1 and 3 statements are true. Second option is 2 and 4 statements are true. Third option, 1, 3 and 4 are true. And the last one is all are true. Okay, it's a straightforward question once again. We have just discussed that in the case of a symmetric matrix, it has to satisfy Aij is equal to Aji. This has to be satisfied. That is what we have seen. So the first statement is correct. We don't have any problem in this one. And for a symmetric matrix, Aij is equal to 0 for I is equal to j, which is wrong. Why it is wrong? Because we have seen that in the case of a symmetric matrix, there is no restriction on a principal diagonal element. I is equal to j simply indicates a principal diagonal element. And there is no restriction on a principal diagonal element in the case of a symmetric matrix. So therefore, the second statement is not correct. Now, for a skew symmetric matrix, Aij is equal to minus Aji is a necessary condition. That is what we have seen. Okay. And even the last statement here is also correct, because if you want a skew symmetric matrix, definitely the principal diagonal elements must be equal to 0, because we have seen that Aij is equal to minus Ji, A11 is equal to minus A11. It will be satisfied only when the principal diagonal elements are 0. So the first statement, third statement and the fourth statements are correct. It means that option C is the right answer. Now let us see the third question. A is a square matrix which neither symmetric nor skew symmetric, and S is 8 plus 8 transpose, D is A minus A transpose. Which of the following statement is true? Both S and T are symmetric, both S and T are skew symmetric, S is skew symmetric and T is symmetric, S is symmetric and T is skew symmetric. So you can pause the video and you can think about it. So I hope you got the right answer. So A is a square matrix. So let us consider a single square matrix which is very simple. A is equal to, let me take 1, 2, 3, minus 1, and we know that this is neither symmetric nor skew symmetric. We know that in the case of a symmetric matrix, A12 will be equal to A21, which is not satisfied. It is neither skew symmetric matrix because in the case of a skew symmetric matrix, the principal diagonal elements are equal to 0. So both of them are not satisfied. So we can use the non-symmetric matrix A, which is also a square matrix here. Now we want A transpose. Now A transpose is nothing but 1, 3, 2, minus 1. Now what we have to look at is the nature of S and D, whether they are symmetric or not. First thing is that S is equal to A plus A transpose. So you can look at A plus A transpose. A plus A transpose is equal to, just add both of them, 1, 2, 3 minus 1 plus 1, 3, 2 minus 1. Try to add both of them. When you add them, that is 2, 5, 5 minus 2. A plus A transpose is nothing but S. So 2, 5, 5 minus 2. Is it symmetric or skew symmetric? It is not skew symmetric because in the case of skew symmetric, the principal diagonal elements are zeros. Is it symmetric? In the case of symmetric, A12 should be equal to A21. A12 is equal to A21, which is true. There is no restriction on the principal diagonal elements. So, only thing is that A12 should be equal to A21, which is satisfied. It means that S is going to be symmetric in nature. So, S is symmetric. Now, what about D? So, D is nothing but A minus A transpose. So, here A minus A transpose, 1 minus 1 is equal to 0. 1 minus 1 is 0. 2 minus 3 is minus 1. 2 minus 3 is minus 1. 3 minus 2 is 1. And minus 1 minus minus 1 is 0. So D is equal to A minus A transpose, which is equal to 0, minus 1, 1, 0. Is it symmetric? No, because in the case of a symmetric, A12 should be equal to A21. A12 is minus 1 and it is not equal to A21. So it is not symmetric. Is it skew symmetric? The principal diagonal elements are zeros, which is the case, and A21 should be equal to minus A12. If you take A12 here, A12 is going to be minus 1. So A21 should be minus of A12. So minus of minus 1 is nothing but 1, which is satisfied. So D is going to be a skew symmetric matrix. So now it means that S is symmetric and D is skew symmetric should be the right answer. Okay. So the learning here is that whenever you have a non-symmetric matrix, now when you're adding the matrix with its transpose, always the sum is going to be a symmetric matrix. So a matrix, when you are subtracting with its transpose, then the resultant matrix is always going to be a skew symmetric matrix. It is always the case. So students, it's very clear that when we have a non-symmetric matrix, A plus A transpose is going to be symmetric. And A minus A transpose is going to be skew symmetric. And even you will observe that A into A transpose, comma, A transpose into A are also going to be symmetric in nature. Okay, so A into A transpose or A transpose into A are going to be symmetric in nature, even though A is a non-symmetric square matrix. So using this particular knowledge, we can write any matrix A in terms of a symmetric part and the skew symmetric part. I can write A in terms of a symmetric part plus the skew symmetric part. So every non-symmetric matrix is going to have a symmetric part inside it and a skew symmetric part inside it. A symmetric part can be written as A plus A transpose divided by 2. And a skew symmetric part can be written as A minus A transpose divided by 2, which can be written using the knowledge of that A plus A transpose is symmetric and A minus A transpose is going to be skew symmetric. So when A plus A transpose is symmetric, A plus A transpose by 2 is also symmetric in nature. When A minus A transpose is symmetric, not skew symmetric, and A minus A transpose by 2 is also going to be skew symmetric in nature. Now if you try to add of both of them, you are going to have A by 2 plus A by 2, which is nothing but A itself. So any non-symmetric matrix can be written as a sum of symmetric plus a skew symmetric part, where the symmetric part is nothing but A plus A transpose by 2. The skew symmetric part is A minus A transpose by 2. So which is a very important point. So students, now we are going to learn about another special matrix which is very important, is an orthogonal matrix. Which is very important for the examination, is orthogonal matrix. Now what is orthogonal matrix? So the condition for a matrix to satisfy the orthogonality is that when the matrix is multiplied by its transpose, whenever you are multiplying a matrix with its transpose, it has to result in an identity matrix. So whenever you are multiplying a matrix with its transpose, it has to result in an identity matrix, which is only going to happen when the transpose is going to be the inverse. We know that A inverse into A is going to be I always. So even A into A transpose, if you want to have equal to Y, which is the identity matrix, this will be satisfied only when the transpose is nothing but its inverse. So A transpose is equal to A inverse. Okay, so whenever the transpose is equal to inverse, then this particular condition will be satisfied. So that is the condition for orthogonal matrix. So we can say a matrix is going to be orthogonal when the transpose is equal to inverse, or A into A transpose is equal to I. We can find the application of an orthogonal matrix inside some matrices called as rotational matrices. Okay, so we are going to use a rotational matrices in the system, so where we require the rotation of a particular input matrix that we are going to give. Okay, so whenever we require a rotation of vectors, which could be the best application of a rotation matrix. So every rotation matrix has to be an orthogonal matrix. So we can check whether a particular matrix is going to be rotational or not by checking its orthogonality. Okay, so every rotational matrix is going to be an orthogonal matrix, which will satisfy the condition the A transpose is equal to A inverse. So just like the way we have written about a symmetric matrix or a skew symmetric matrix, we can also write about a particular orthogonal matrix. It means that when you know the properties of an orthogonal matrix, we can definitely write any matrix that we know whether it is going to be orthogonal or not. Directly by looking at it, we can say whether it's going to be orthogonal or not. So for that, I want to test your vectors. When can we say the two vectors A and B are going to be orthogonal? The two vectors A and B are said to be orthogonal when their dot product is equal to 0. Yes or no? The two vectors A and B are said to be orthogonal when it satisfies the condition that their internal product or a dot product should be equal to 0. For example, let me have the A which is equal to I plus J. Let me take B is going to be I minus J. Now what is the dot product? The dot product is equal to 0. This is what we call as the orthogonality of a matrix. Orthogonality of a vectors. A dot B is equal to 0 or nothing but orthogonal vectors. We have something also called as orthonormal vectors. So in the case of an orthonormal vectors, we'll observe that when you have two vectors A and B are orthonormal, provided first thing is that they have to be unit vectors. It means that the mod of A should be equal to the mod of B should be equal to 1. The magnitude of the vectors should be equal to 1. It means that they have to be unit vectors. And the second thing is that what we have seen is the orthogonality, that the product of these two vectors should be equal to 0. The dot product of the two vectors if it is equal to 0. So the two conditions have to be satisfied along with the orthogonality. One more additional condition is that they have to be unit vectors in the case of a orthonormal vectors. Now how can we have a unit vector for A? We can find the unit vector for A by simply writing it as I plus j by its magnitude, which is nothing but root. Now if I take this as equal to A and B 1 minus j divided by I minus j divided by root. Now if you observe, these two are going to have unit vectors because now their magnitude will be equal to 1. I plus j divided by root 2 and I minus j divided by root 2. How I got the idea whether they are unit vectors or not? I have seen the vectors here that I plus j, their magnitude is going to be equal to root 2 and I minus j is also going to have a magnitude is equal to root 2. Any vector when you are dividing by its magnitude, it is going to give you the unit vector. So that's what I have written here. Now I am directly writing A bar is going to be equal to I plus j by root 2 and I minus j by root 2. Now the dot product is equal to 0 and their unit vectors, and these vectors are going to be the orthonormal vectors. Now why are we learning about orthonormal and orthogonal vectors? Because we have to understand the property of a orthogonal matrix. And we observe that in the case of an orthogonal matrix, it has to satisfy their rows and columns, or rows or columns have to be orthonormal vectors. Rows or columns have to be orthonormal vectors. For example, after learning about orthogonal and orthonormal vectors, now if I write the matrix A, we know that these two are orthonormal. I can write I by root 2, j by root 2. So directly I'll write it as 1 by root 2, 1 by root 2. I by root 2 minus j by root 2, I will write it as 1 by root 2 minus 1 by root 2. So this is how slowly I'm writing the vectors as matrix. Now if you observe, this is a vector, this is also a vector. So these two vectors are orthogonal matrix, orthonormal vectors. Now when I'm writing them in terms of a matrix, now it is going to become a orthogonal matrix. If I can bring the root 2 outside, then it is 1 by root 2 into 1, 1, 1 minus 1. Now this matrix is going to be a orthogonal matrix. So in this way I can write any matrix as a orthogonal matrix. Okay, for example, if I have 2, 1, now 1 minus 2. Now you can see that if this is a vector, this is also a vector, their product 2 into 1 plus 1 into minus 2 is equal to 0. It means that it is satisfying the orthogonality. Okay, if I consider it as 2i plus j and I minus 2j, now the dot product is equal to 0. It means that they are orthogonal vectors. But we know that rows and columns of an orthogonal matrix are orthonormal vectors. So it is not only satisfied with the orthogonality of vectors, that is not sufficient here. They have to be having the unit vectors. Now you can see that here 2, 1. So 2i plus j is going to have a magnitude is equal to root 5. So divided by the magnitude, then you are going to have orthonormal vectors. So they divide this one by root 5. So 2 by root 5. And here also divided by root 5. Here also it is going to have an identical magnitude. Now bring the root 5 outside. Now you'll have 2, 1, 1 minus 2. This is also a orthogonal matrix. Now how to test whether it is going to be orthogonal or not? Matrix multiplied with transpose should be equal to an identity matrix. You can check with the first one. We have to check A into A transpose whether it is equal to I or not. Right? So A, which is 1 by root 2 into 1, 1, 1 minus 1 into its transpose, which is 1 by root 2, 1, 1, 1 minus 1. So 1 by root 2, 1 by root 2 is nothing but 1 by 2. So 1, 1, 1, 1. It is going to be 2 here. 1 into 1 is going to be 1 minus 1, 0, 0 and 2, which is equal to 1, 0, 0, 1. So it is going to satisfy the condition of orthogonal matrix. So just remember that whenever you are writing an orthogonal matrix, they have to satisfy that when you are multiplying their rows. Okay, when you are multiplying their rows directly, okay, their elements when you are multiplying, it means that it has to satisfy the orthogonality condition and also orthonormality condition. Orthonormality is nothing but their magnitude should be equal to 1 and the dot product should be equal to 0. So any such matrix is going to be a orthogonal matrix. So just by looking at it, whether you are satisfying the condition or not, that is secondary. Just by looking at the matrix, we can say whether it is going to be an orthogonal matrix or not. So the question that is given here is that determinant of an orthogonal matrix, first statement is 1, second statement it says that determinant is equal to minus 1. The options given are statement 1 is true, option B is statement 2 is true, option C is both are true, and option D is none of them is true. Okay, so you can pause the video and try to solve it. So I hope you got the answer. We know that the condition to satisfy the orthogonal matrix is that A into A transpose is equal to I. A into A transpose is equal to I. Now apply determinant on both sides. So when you apply the determinant on both sides, so you have A into A transpose determinant. So whenever we have a mod of AB, this will be equal to mod A into mod B. So using this logic, we can write it as mod A into mod A transpose is equal to the determinant of a identity matrix is nothing but 1. And we also know that the determinant of transpose will be equal to the same matrix. So by that logic, I can also write it as mod A whole square is equal to 1, which implies that the determinant of A is equal to plus or minus 1. The determinant of A is going to be equal to plus or minus 1. It means that both are true. So the answer is both A and B. The answer for this problem is both A and B are And I've already told you that the application of the orthogonal matrix is going to be in terms of rotational matrix. Okay, the rotational matrix is going to be the best example or the best application of a orthogonal matrix. So a rotational matrix is always going to have the determinant is going to be always equal to 1. Okay, it's not even minus 1, it has to be equal to 1 in the case of a rotational matrix. So rotational matrix is an orthogonal matrix whose determinant is equal to 1 always. So what is the example? For the rotational matrix example, the two-dimensional rotational matrix R of theta can be written as equal to that of cos theta minus sin theta cos theta. So this is an example of a rotational matrix. Cos theta minus sin theta cos theta will satisfy the condition of orthogonality, and even if you observe, the determinant is equal to 1 in this case. Now similarly, the determinant of A is equal to minus 1 finds its application in the reflection matrix. So there is a matrix called as a reflection matrix, which is going to be the reflection of a particular vector. Okay, so that particular matrix is going to have the determinant is equal to minus 1. Okay, and of course it has to be a orthogonal matrix. Now let us write a question, one more question on a orthogonal matrix. So this is also a gate problem. So you can try to pause the video and solve it. So I believe you got the right answer. So you have a matrix and it is given that it is a orthogonal matrix. You have to just find the value of x. So one way to do it is that you can multiply the matrix with its transpose and equate it to an identity matrix. So 3 by 5, 4 by 5, x and 3 by 5 into the transpose is going to be 3 by 5 x, 4 by 5, 3 by 5, and this will be equal to the identity matrix 1, 0, 0, 1. So if you consider the first element, probably there is no use of considering the first element. So I will consider the second element. So the second element is going to be 3 by 5 to this one. So 3 by 5 into x plus 4 by 5 into 3 by 5 should be equal to 0. So it is very clear that the value of x should be equal to minus 4 by 5, because if you take 3 by 5 as common, the value of x should be equal to minus 4 by 5, which is very simple. Or you can just look at the question and say the answer, because 3 by 5, 4 by 5, x and 3 by 5, when you multiply the rows, the value should be equal to 0. So 3 by 5 into x plus 4 by 5 into 3 by 5 should be equal to 0. It means that the value of x should directly be equal to minus 4 by 5. Okay, you can just look at it and say the answer here, because only when the value of x is equal to minus 4 by 5 that the multiplication of rows should be equal to 0. So the answer is option D, minus 4 by 5. Now students, let us discuss about the complex matrices. So whatever we have discussed in the case of real matrices, now we are going to look at the case of the complex matrices. Now complex matrix is a matrix whose values are going to be the complex numbers. Now in that, the first type of the special matrix that we are going to look is a Hermitian matrix. The first type of matrix that we are going to look in the case of a special matrices is a Hermitian matrix. Now what is the meaning of a Hermitian matrix is that just like the case of the symmetric matrix that we have seen, that is nothing but A transpose is equal to A. In the same way, the transpose of a conjugate, which is nothing but A theta, if it is equal to A, it means that the transpose of a conjugate, if it is equal to the matrix itself, we can say the matrix is going to be a Hermitian matrix. Now we know A theta is nothing but A bar whole transpose should be equal to A. Now when you take a matrix A, which is Aij m by n, okay, it is taken for granted that it has to be a square matrix, because when you are equating these two, it means that their order should be same. It will only happen only when the matrix is a square matrix. So, and B, A bar whole transpose, which is nothing but A theta, which is A ji bar. Okay, see, I am writing it as m by n, but the values of m and n are same for the reason that it is a square matrix. So by which it's very clear that the value of Aij is equal to Aji bar. Aij is equal to Aji bar. Now the way we have written a symmetric matrix, in the same way we can write the Hermitian matrix also. Just by using this particular property, we can write that any matrix that it is going to be a Hermitian matrix. So if you observe Aij is equal to Aji bar, when the value of I is equal to j, and let me consider I is equal to j is equal to 1, it means that A11 is equal to A11 bar. And the same way, A22 is equal to A22 bar, A33 is equal to A33 bar. So the first important thing here is that the principal diagonal element should satisfy A11 is equal to A11 bar. When is it going to happen? For example, if any element A is going to be plus j, which is a complex number. Now if A bar is going to be 1 minus j. Now if I say that A is equal to A bar, which is not the case here, but that will happen only when you don't have the imaginary part, or it will happen only when the number is going to be a real number. So it indicates that in the case of a Hermitian matrix, always the principal diagonal element has to be a real number. So Aij for I is equal to j has to be a real number. Okay, so Aij has to be a real number. Okay, so whenever you are considering a principal diagonal element has to be a real number. Now, of course, the remaining A12 should be equal to A21 bar, or A21 is equal to A12 bar. A21 is equal to A12 bar, and similarly A31 is equal to A13 bar. A32 is equal to A23 bar. So we can write the matrix. So the principal diagonal elements have to be real numbers. So they can be any real numbers. Now the moment I write the A12, so if the value of A12 is 1 plus j, A21 should be its conjugate. So 1 minus j. So this is going to satisfy the property of, okay, the Hermitian matrix. That is, the A theta is equal to A, or the transpose of a conjugate of a matrix is equal to the matrix itself. Now this matrix will satisfy the condition of A theta is equal to A. We can verify it. First of all, you consider conjugate. The conjugate is nothing but 4, 1 minus j, 1 plus j, 5. Now the transpose of it is equal to 4, 1 plus j, 1 minus j, 5, which is equal to. So the next one is a skew Hermitian matrix. So just like a skew symmetric matrix, even in the case of a skew Hermitian matrix, A theta is equal to minus A. There in the case of a skew symmetric matrix, A transpose is equal to minus A. Here the value of A theta is equal to minus A. So when you consider a matrix A, which is Aij, m by n, where m is equal to n, now A theta will be equal to the of A ji bar n by m. Now when you equate A theta is equal to minus A ji bar is equal to minus Aij. Ji bar is equal to minus Aij. This is the condition that has to be satisfied. Now once again, if you look at the principal diagonal elements, let me take the value of I is equal to j is equal to 1. So A11 bar is equal to minus A11. Now can you tell me when this is going to be satisfied? That A11 bar is equal to minus A11. This will be satisfied only when the A11 itself is going to be an imaginary number. Now for example, the same example, for A is equal to 1 plus j, A bar is equal to 1 minus j. So when you want to say that A bar should be equal to minus A, this will be satisfied only when you don't have the real part. So if you don't have the real part, then it is automatically satisfying. A bar, which is minus j, is equal to minus A. Okay, so for a number, for its conjugate should be equal to the negated number. The condition is that the number itself has to be an imaginary number. So the principal diagonal elements have to be imaginary numbers. So when I am talking about the PD elements, the principal diagonal elements, they have to be imaginary. Now the remaining elements, A21 should be equal to minus A12 bar. So what does it mean here? It's not only a conjugate with a minus sign. A12 should satisfy, it should be equal to that of minus A12 bar. A31 should be equal to that of okay. Then form the matrix. This time let me take the 3 by 3 matrix. The principal diagonal elements should be the imaginary numbers. So I can take 7j, 3j and 2j. They are imaginary numbers. They can be zeros also, it doesn't matter. Now, if I have the number here is 1 plus j, here it should be the conjugate with a minus sign. So if it is 1 plus j, the conjugate is 1 minus j with a minus sign, it is going to be minus 1 plus j. If I have a 2 plus 3j here, the conjugate is 2 minus 3j, the minus is going to be minus 2 plus 3j. If I have 3 minus 4j as the element, the third column, the second row, so A23, then A32 is going to be equal to the top conjugate with a minus sign. Conjugate is going to be 3 plus 4j with a minus sign, it's going to be minus 3 minus 4j. Now this matrix is going to be a skew Hermitian matrix. So the last one is a unitary matrix. So it is just like what we have discussed as an orthogonal matrix. So in the case of a unitary matrix, A into A theta is equal to I, which implies that A theta should be equal to its inverse. So the example that we can have is that 1 by root 2, 1 plus j, 1 minus j, 1 minus j, 1 plus j. So this will satisfy the topic of a unitary matrix, which is nothing but A into A theta is equal to I. Okay, so with this topic we can end the session. Hope it is very interesting for you, and it's very important, especially the real part. What we have seen is a symmetric and skew symmetric is very, very important for the examination. The complex part is not very important for the examination. Right? So this is going to be a very important topic in the case of GATE examination. Okay. With those words, I'm concluding the session. Thank you.